At Northrop Grumman, innovation isn't just an idea. It's a way of life. The value of performance. Northrop Grumman.
Good afternoon to all of you. Delighted to see you here. Glad you're getting a day out of regular school to be here, and hoping to say a few things that might be of interest to this distinguished group of budding scientists here at X-STEM. So I thought I might talk to you a little bit about sort of pathways in scientific professional careers, because I think a lot of you who probably have some interest in science aren't quite sure yet where that's taking you. And maybe you're a little nervous that you haven't really felt that calling strike you like a bolt of lightning to say, that's what I want to do. You're kind of interested. There's a lot of things maybe that are appealing to you, including things that have nothing to do with science. And maybe there are a few people around you who seem to have it all together and know exactly what path they're on, and you're feeling a little uneasy about why that hasn't happened to you yet. Well, take it easy, because it didn't happen to most of us either until quite a bit later. And I'll tell you my own story, and you'll see just how much later it was before things started to fall into place, even though there were a lot of interesting twists and turns along the way. So we're looking at this question of career, and this picture makes it look as if it's a nice straight pathway and there's no question about where it's going. And again, that's not been my experience. So let me start a little ways back. When I was a kid on a small farm about 3 hours from here, growing up, wondering what I want to do with my life. Yeah, that's me. Yeah, that was my barn. I'm not showing you the rest of the place, but let's just say there wasn't any indoor plumbing, and you get the idea. So what was I standing there thinking at this age about what I wanted to do with my future? I'll tell you what I was thinking. I wanted to drive a truck, and the bigger the better, because that would be a really opportunity to see how machinery could take me where I wanted to go. But, you know, time went on a little bit. I had some other ideas, grew up a little bit, got to be, interested in the opposite sex, and wanted to be sure I was doing something that was appealing. So I decided, okay, I'll be a musician. I'll be a country music star. Yeah, that's it. Well, that didn't work out so well. But along the way, some other things caught my attention. I like math, but I really liked the idea of the things you could learn using chemistry. So I was one of those kids who convinced my parents to get one of those chemistry sets, and yes, we did have an explosion or two, but it got me to the point of thinking, this is science that you can actually not just read about, you can do. So after high school, I decided I'll go and get more training in chemistry, and off I went to the University of Virginia, not far from here, and there I met Carl Trindle, who was my research mentor and who for the first time gave me a project that was real cutting-edge science and expected me to do it. And it was really tough and really interesting. And I got hooked because I kind of figured he was right. The chemical bond is the coolest thing. So what should I do? Well, I should go to graduate school. Off I went to Yale University, pictured here, to learn how to do chemistry in an even more elaborate and somewhat theoretical way, because my part of chemistry was the part that related to how you understood things mathematically. So for my time in New Haven, the thing I was most in love with was this. Doesn't that just make you want to jump up and shout? Second order differential equations, what could be better than that? And that was cool, but after a couple of years, I realized I'd been a little narrow in my approach to science. I hadn't paid any attention to biology at all. Frankly, the way biology was taught in my high school was mind-numbingly boring, and it just didn't seem like anything that was worth spending time on. It was all descriptive, didn't seem to have any principles. So I took a course in biochemistry just to see what I might have missed, and I was blown away, because there were principles, things like genetics, things like DNA and RNA, and you could figure stuff out if you knew some of those principles, and you kind of had a feeling that we were on the brink of a pretty major series of steps forward in understanding how life works and how disease occurs and how we might do something about that. And so this guy, who by then is a graduate student, already married with a little kid, began to think, you know, maybe what I really want to do is the kind of science that is biological and where I'd have the chance to apply what I'm learning in a way that could help somebody who has a sickness of some sort. So Molecules of that sort might be interesting. More complicated molecules might be interesting, but the most important and exciting molecule emerged in my consciousness is DNA. And I had to go and study DNA, and I had to do it in a way that maybe it could lead to something medically beneficial. And frankly, I had had very little ideas about being a physician until that point, and I'm already past 20 years old. So big turn, and off I went to the University of North Carolina to medical school to learn how to be a doc. But I still really liked the idea of being able to apply science and research to figuring out answers to questions that medicine didn't have yet, and there were plenty of those, and there still are today. And so I looked for opportunities maybe where science might be able to shed light on a vexing medical problem. And one of the patients I took care of was a young woman who had a diagnosis of cystic fibrosis, which is supposed to be a childhood disease, but here she was in her early 20s, just now getting diagnosed, and I wondered, what was that about? And I read what I could about cystic fibrosis, and it was pretty clear that nobody really knew what caused this disease, other than it was genetic. Nobody knew what gene was actually responsible, what gene was misspelled in the course of the disease. And that seemed like a really important problem to work on someday. So I went off and did a fellowship learning more about human genetics. I took care of patients with genetic diseases, patients like Meg Casey, this young woman with progeria, the most dramatic form of premature aging. And I got really puzzled about that too and wondered how could that be studied someday to come up with answers for these kids and young adults whose bodies were aging at about 7 times the normal rate, even though their minds were completely clear, in fact, oftentimes precocious. So it seemed like there was something here that might be interesting to do. So off I went at that point to become a researcher in human genetics, and I got a job ultimately at the University of Michigan and worked on trying to find the causes of those diseases like cystic fibrosis or progeria for which we had no answer, recognizing that this was a really tough problem because that meant you were looking for something as subtle as a single base pair, a single letter of the DNA code that's misspelled in a very large sea of information, namely the human genome with all of its 3 billion base pairs. And it was pretty frustrating. I spent several years making absolutely no progress. One of the problems was it was difficult to travel around the genome in anything other than baby steps. So one thing that I did was to try to figure out how to go more quickly, develop something called chromosome jumping, here cartooned with a frog. We didn't use frogs, actually. We used recombinant DNA. But it did make it somewhat easier, if you were looking for a gene like that for cystic fibrosis, to get there in less than 20 years. And I figured I had to have a metaphor about what I was doing to explain why it was taking so long. So I would do things like go to a farm and hold up a needle in the middle of a haystack to explain why this is so hard, people. That's why I haven't got the answer yet. But ultimately, with the help of a lot of really talented graduate students, postdocs, and other collaborations that I was able to develop, things started to work. And we found the gene for cystic fibrosis in 1989. And we found the gene for Huntington's disease as part of a collaborative team in 1993. We found the gene for neurofibromatosis, sometimes called the elephant man disease, in 1990. And much more recently, in 2003, the gene for Hutchinson-Gilford progeria syndrome. Here you see this young man, Sam Burns, affected with that disease, who became a very good friend of mine. But then something happened. I wasn't ever expecting that I would end up in any place other than a university, taking care of patients, doing research, teaching medical students. That seemed like my calling. But then another calling seemed to happen because at this point, the Human Genome Project was just getting off the ground. It was 1992. Bernadine Healy was the director of the National Institutes of Health. She had hired none other than Jim Watson, as in Watson and Crick, to come and get the Genome Project started. But let's just say they had a bit of a clash of personalities. And before anybody could blink, suddenly Watson was gone, and Bernadine was making a call. And she was saying, the Genome Project is just getting started. It's going to be maybe a 15-year effort. We need somebody to come to the National Institutes of Health to run this program. And I said, I have no idea why you're calling me. Surely there must be other people who could do this. And she's like, nope. You're the one that I think has the experience with both medicine and research that you could do this. So I talked to people I knew, and I talked to my mom. And my mom said, you know, the one thing that I have always hoped for my sons is that none of them would ever go into government service, so don't do it. So I said to Bernadine, sorry, it's not me. And then I began to wonder, what am I doing here? There's only going to be one human genome project in all of human history. And here's the chance. And I could have the chance to help steer that ship with all these other amazing people that are lining up to work on it. How can I walk away from that? Well, she called again. And this time I said, yes. My mother was horrified. She ultimately decided it was okay, but for a long time there, she was like, I don't know what I did wrong, that one of my sons is doing this kind of thing, becoming a federal employee, oh my God. But that meant I had to move all of my research efforts from where I had been at Michigan and bring them to the National Institutes of Health up the road here in Bethesda, Maryland, and both run an institute and also set up a laboratory because we needed to have that kind of capabilities there. In the Bethesda campus, and that was a lot of fun, recruited a lot of smart people to come and join this visionary effort. But a lot of what I did, which I'm not going to show you, you'll be glad to know in each one of the icons on this diagram, was to run the Human Genome Project, this incredibly bold, audacious effort to read out all 3 billion letters of the human DNA instruction book, and to do it in a 15-year timetable, which had been promised by Watson and others before we had really much of an idea about how to do it, which meant we had to invent all kinds of technologies and make them appeal quickly to various people to adapt, and then scale them up, because ultimately we had to derive about 1,000 letters of the DNA code every second, 7 days a week, 24 hours a day, in order to get this done. Well, that took 2,500 scientists, 20 research institutes from 66 different countries. It was my job to be the project manager, the field general, the overall definer of what the strategy was going to be. It was a wild ride, and it had ups and it had some significant downs, but ultimately we all got to go to the White House and say, we did it, on June 26, 2000, to say we have a draft, and then shortly after that, the publication of that draft in Nature magazine, The Human Genome. And in 2003, just about 11 years ago, this month, we're able to say we have completed all of the goals of the Human Genome Project 2 years ahead of schedule, and Congress was glad to hear this part, $400 million under the budget that had been projected. So that was good, but of course that wasn't the end of the story. We had the sequence, we had these great people who had worked on it, all of these folks and the teams that had made this possible, but we had other things we wanted to do with the information. How do you apply it to cancer? How do you apply it to drug development? How do you go beyond one genome to thousands of them? How do you figure out how the genome functions? How do you understand the 0.1% of DNA that differs between us in a way that gives us insight into disease risk? So that was the next step, and I plunged into that with all of these other incredible people working alongside, and this has gone really amazingly over the course of the last 11 years. But then I decided, okay, I've been doing this thing for a while. 15 years is long enough. I'm going to basically step away into the white space and do something else. I don't know what it's going to be. So they had a nice party for me. I got to play the guitar with a band, and we all said, okay, that's it. Another person will step in and start running genome research. And that was cool. I got to play my guitar. By the way, notice, please, the motif on the fretboard. No, that is not serpentine wall. That is a double helix in mother of pearl. Very nice custom guitar that my friends at the Genome made it possible for me to design. I got to ride my motorcycle with my wife, which I hadn't been doing a lot of for a while there. I got to write a book about DNA and personalized medicine and how all of the things that were happening with the discovery of genomics were making a difference. But then there was another phone call. And this time it was a different person calling saying, you need to come back. And yes, it was the president, and yes, it was time to return, this time as the NIH director. A great honor, an enormous privilege to be able to stand at the helm of the world's largest supporter of biomedical research, to try to make the most of the $30 billion that the taxpayers provide every year for this effort to try to make discoveries about how life works, how disease happens, and what we could do about it. So yes, I packed up my briefcase and went back, and I have now been there for the last 4.5 years, overseeing this really remarkable enterprise, and it is remarkable indeed to see the things that are possible. I also keep my lab going, and that's been a good source of mental health for me during this time, and those are the folks who work in my lab right now. My lab is working on diabetes and on that disease called progeria, that form of rapid aging. And it's been very gratifying as time has moved along to see medical research in genetic diseases moving beyond the discovery of the cause to identifying interventions that actually work, treatments. I mentioned cystic fibrosis way back in 1989, finding that gene, hoping that that would someday help somebody. Well, boy, is that happening now with the development of drugs that are specifically based upon a molecular understanding of the disease, built upon that gene discovery. We have, in some instances, drugs that are available for people who are really getting into serious trouble from this disease, who are now back at work, back at school, feeling as if they've just bought a new lease on life. So way to go, Lindsay and all the others. And that disease, progeria. My lab, working in collaboration with others, able to identify a possible therapeutic for this. A drug that had been developed for cancer, didn't work all that well for cancer, but turned out to have just the right properties to treat this disease. And sure enough, it was possible in the clinical trial to show that this shows benefit for kids in terms of slowing down the cardiovascular disease that ultimately takes their lives. And Sam Burns, my buddy who you saw the picture of, probably extended his life an extra 4 or 5 years as a result of that. Sadly, Sam died 2 months ago, which means we have much more work yet to do to figure out how to do better for this disease. But we're on a roll getting started anyway. And lots of other diseases. This is an example of cancer, where a new drug that's targeted specifically for the mutations in that person's cancer, so-called precision medicine, is resulting, if you go from left to right in those x-rays, in dramatic melting away of tumor as a result of treatment with this drug called Xalkori. Another example here where kids with leukemia who had failed all forms of therapy now being treated with cancer immunotherapy, activating the immune system to go after the cancer cells. Or in this case, using DNA sequencing to find the cause of a very rare condition that affected these two twins, giving them the opportunity to have pretty much a normal future from where they had been, both of these, especially the girl, very close to the point where their parents were about ready to give up that they had any future at all. So advances are happening with great speed. All of you who are interested in science, I would really want to encourage you to look at the opportunities in biomedical research. This is an exhilarating time. The acceleration of the ability to ask and answer questions has never happened at this level. And so we want you to come and join us and be part of that grand adventure. You'll work with other teams. You can use all kinds of different forms of science, from computer science to imaging to nanotechnology to biology to medicine. But together, we're going to figure out how to cure cancers, how to cure Alzheimer's disease, what to do about diabetes, rare diseases, common diseases. That all looms ahead of us, not so quickly that you'll miss out on it, because the good stuff is probably still 10 or 20 years ahead. But we would love it to have the best and brightest in this nation and outside this nation come and join this enterprise. What am I going to do next? Well, gosh, I don't know. I'm still having a pretty good time doing what I'm doing, but eventually I guess it'll be time to move on to something. Maybe I'll try to make it as a musician, as long as I have somebody beside me like Cookie Monster, or maybe somebody like Joe Perry, the lead guitarist of Aerosmith. Well, probably be a little hard to convince him to do anything other than just take a picture for this poster. Or maybe I'll just ride my motorcycle, or maybe, finally, I'll get around to doing what I really wanted to do, which is to ride that truck. Thank you all. Before I leave, you're going to get subjected to one more thing. And does anybody know what tomorrow, April 25th, is? DNA Day. It's also Arbor Day, I think, but it's DNA Day. Come on. So why is it DNA Day? Why do we pick April 25th? Because I like it, somebody says. Well, I do now, but actually, 1953, Nature magazine, April 25th, the most significant paper in biology of the century, Watson and Crick, The Structure of DNA. There it was. So ever since, April 25th has kind of brought DNA to mind. So it's brought to my mind that we ought to have a song about DNA today. So imagine, now that I can actually determine the complete DNA sequence of any of your genomes for $1,000, and that's the price we're down to now. Imagine that. Used to be hundreds of millions. Imagine that you just got yours. And you know, I sent it to you, and you open up your iPad, and there it is. Oh my gosh, 3 billion base pairs. A, C, G, T, T, A, G. What does that mean? So you're there staring at it. You're trying to figure out, what is this all about? You might sing a song like this one. And by the way, this has a little bit of a chorus thing, and it's at the point where I have to sing a high C sharp, and it's not easy for me to reach a high C sharp. So I would appreciate a little group support at that point. You will know it, you'll feel it, that it's time to help out Dr. Collins. So here you are, staring at your iPad screen, trying to figure out how to make sense out of all this DNA sequence, and this is your song. As I walk along the bases in all 3 billion places upon my iPad screen, am I built for strong endurance or loss of life insurance? Am I a mere machine? I'm a walking through the genes, don't know what all this means. Oh, what can the meaning be behind that G and T? And I wonder, help me now. Why wonder why? Why? You've got an A, I've got a C there. What does that say? Amazing DNA, a D-D-D-D DNA.